In this lecture, we discuss about curve tracing. So let us first take what is the history of curve tracing in modern mathematical science. Curve tracing dates back to ancient Greek mathematics, where mathematicians like Euclid, Archimedes studied geometric curves. However, the systematic study of curves gained prominence with René Descartes and Pierre de Fermat in the 17th century, who introduced coordinate geometry. Later, Isaac Newton and Gottfried Wilhelm Leibniz developed calculus, which provided powerful tools for analyzing curves using differentiation and integration. In the 18th and 19th centuries, Joseph Louis Lagrange and Carl Friedrich Gauss contributed to curve analysis through differential equations and geometry, making curve tracing an essential part of mathematics and engineering. So this is about the history of curve tracing. Let us try to define what is the meaning of curve tracing. So before discussing about the curve tracing, let us see what is the meaning of curve tracing. Curve tracing is the process of studying and sketching a curve based on its mathematical equation, usually given in Cartesian, polar, or parametric form. This is a process. Curve tracing is the process of studying and sketching a curve based on the mathematical equations, and that equation may be either Cartesian equation, polar equation, or parametric equation. It involves analyzing key characteristics like symmetry, asymptotes, intercepts, maxima and minima, concavity, and inflection point. This method helps in understanding the shape and behavior of curves without plotting numerous points manually. So this is the typical definition of curve tracing. Let us take some basic things in curve tracing. The first thing, what is the meaning of curve plotting? The curve plotting and curve tracing both are two different terminologies. Curve plotting means finding the exact shape of the curve is called plotting of curves. Let us take one example. Now let us try to plot the straight line x plus y is equal to 2. So for that purpose, we have taken a graph paper in which we have taken the value of x, y is 0. Then we are, if y is 0, the value of x is 2. So first point is 2, 0. Similarly, if we put x equal to 0, then the value of y is 2. So we have the second point. And if we join this 2 point, then we get the exact line x plus y is equal to 2. So uh, this type of process in which we get the exact shape of the given curve is called curve plotting. Now, what is the meaning of curve tracing? Finding the approximate shape of the curve is called curve tracing. Let me take one example. Suppose we want to draw the circle x square plus y square is equal to 4. So we do not want to measure this radius. This radius should be 2. If we write down this is 2 square. So this is the equation of circle whose radius is 2. So this radius may be 2.5, it may be 1.5 or 2.15 or 1.75. So this radius may not be fixed, but we have the approximate shape of the circle whose radius may be not exactly 2. So such type of finding the approximate shape of the curve is called curve tracing. Then the next basic points based on the curve tracing is called singular point. What is the meaning of singular point? An unusual point on a curve is called a singular point. Unusual means that is not usual point as usual point. Let me take one example over here. We have given a curve. Let us try to draw tangent at 1, 0. If we want to draw the tangent at 1, 0, what will happen? What is the meaning of tangent? Tangent is nothing but a line which touches the given curve only at one point. But now here we want to draw the tangent at this point 1, 0, and at this point tangent will cross the given curve. Tangent will cross the given curve. So this type of point where the curve behaves unusual behavior, so that is called unusual point or singular point of the given curve. The next thing is the point of inflection, a point where the curve unusually crosses its tangent is called the point of inflection. So here clearly this 1, 0 is the point of inflection. The next thing is the multiple point, a point through which more than one branches of a curve pass is called a multiple point of the given curve. For example, just look here, this at the point O, just look here, there are two branches of curve. This is the one branch of the curve and this is the another branch of the curve. Two branches of curve pass through. So such type of point is called multiple point. And if it has more than two, suppose three branches, four branches, five branches, and so on, so that is called multiple point. So since here there are only two branches of the point, two branches of the curve, so this point is called double point. So let me go ahead. What is double point? A point on a curve is called double point if two branches of the curve pass through it. It is of two type. The type number one, which is called node. What is the meaning of node? A double point is called node if the branches of curve passing through it are real and the tangent at the common point of inflections are real and distinct. So just look here. If we want to say that this is node, what it means? So here we are able to draw this is the one tangent and this is the another tangent. So we can draw the two real tangent which are real as well as distinct. So such type of double point is called node, where we can get the two different tangent on the two different branches and both the tangents are real and distinct. The another double point is called cusp. A double point is called cusp if the branches of curve passing through it are real and tangents at the common point of intersections are coincident. Let me take that example also. So this is the point at which there are two branches of curve. This is the one branch and this is another branch. And if you want to draw the tangent at this point, this x-axis is the tangent. So clearly this x-axis is tangent for this branch of curve as well as this branch of curve also. So for both the branches of the curve, we have one common tangent. So this is called cusp. This point is called cusp. This double point is called cusp. Similarly, we have triple point. What is a triple point? A multiple point is called triple point if three branches pass through the given point. That is called triple point. So we can also write down fourth point, fifth point. So now this may be, that's why this is called multiple point. Now there are different types of curves. The first types of curve is called Cartesian curve. An equation of curves which contains the Cartesian coordinate x, y is called Cartesian curve. It has of two types. The first one is called explicit curves. An equation of curve in which the variables can be separated is called explicit curve. It is represented by y is equal to f of x. So here we can say that with left hand side is a function of y and right hand side is a function of x. So here we are able to separate the variables. Now the second is called implicit curves, an equation of curve in which the variables cannot be separated is called implicit curves. It is represented by f of xy equal to 0. Let me take example for this. Suppose if we write down y is equal to 2x plus 3. So this is what it is called explicit curve where the left hand side is function of y, right hand side is function of x. And now suppose if I will write x square plus y square plus xy equal to 0. So here we are not able to separate x and y. So such type of curve is called implicit curves. The second type of curve is called parametric curves, an equation of curves in which two or more variables can be expressed in the form of one variable is called parametric curve. It is represented by x is equal to f of t and y is equal to g of t. This is called parametric curve. X and y are represented by only one variable t. The third curve is called polar curve. An equation of curves which contains the polar coordinate r theta is called polar curve. It has of two types. The one is called simple polar curve. Any relation between r and theta is called polar curve, and rose curve is the second type of polar curve which can be represented by either r equal to a sine n theta or r equal to a cos n theta. This type of curves are called rose curves. So this is the different types of curves. Now let us take what are the different applications of curve tracing. So it has applications in engineering design. Engineers use curve tracing to design roads, bridges, and tunnels, ensuring smooth transitions and stability. The second application of curve tracing is in physics, especially in motion and trajectories. The motion of objects like projectile, planetary orbits, and wave patterns follow specific curves that can be studied using curve tracing. The third application is in aerodynamics and fluid mechanics. The study of airflow over wings, fluid motion in pipes, and shock waves relies on tracing curves representing velocity and pressure changes. The fourth application is in computer graphics and animation. Curves like Bezier curve are fundamental in graphic design, animation, and game development for smooth motion and shape modeling. The fifth application of curve tracing is in robotics and path planning. Robots use curve tracing in trajectory planning to navigate through obstacles and reach targets smoothly. Now, the next application is in signal processing and communication. Waveforms in electrical circuits, sound waves, and communication signals follow specific curves analyzed using curve tracing. The seventh application is in economics and optimization. Economic functions like cost revenue curve and supply demand curves are analyzed using curve tracing to make informed decisions. The eighth application is in medical imaging and biomechanics. In medical fields, curve tracing helps in analyzing body motion, heartbeat waveforms, and MRI or CT scan data. Ninth application are is in of the curve tracing is in structural analysis. Engineers study stress, strain curves to determine the strength and flexibility of materials used in construction. The next application is in astronomy and space science. The paths of comets, planets, and satellites are analyzed using curve tracing to predict celestial movements and design space missions. So these are some particular applications of curve tracing. These are not limited to only these 10 applications. There are a lot of applications of curve tracing. Thank you.